Imagine a top-secret, multi-billion-dollar wartime facility, where the stakes are, quite literally, the survival of the free world. It is late 1944, deep in the remote, dusty desert of Washington State. The United States government has just powered up the massive B reactor at Hanford. This is not some small university chemistry set. This is the absolute leading edge of the Manhattan Project. Standing right there and overseeing this unprecedented machine are the brightest, most celebrated minds on the planet. Giants of physics, men like Enrico Fermi and John Wheeler. They throw the switch. The control rods are pulled back. The chain reaction begins, the dials climb, and then it just dies. Inexplicably, the massive nuclear fire just sputters out and completely suffocates. It is like building the most expensive, most complex bonfire in human history. Striking the match, getting this roaring, blinding flame, and watching it mysteriously choke itself to death. Nobody knows why. Enrico Fermi, the man who basically invented the nuclear age, is completely baffled. John Wheeler is stumped. They are terrified, staring at this paralyzed machine, knowing that if they cannot fix this, there is no plutonium. And if there is no plutonium, the atomic bomb project fails. The panic in that room is suffocating. So, who swoops in to solve the mystery and save the entire project? It isn't a senior statesman of physics, nor an allied general. It is a young Chinese immigrant, a woman who wasn't even allowed at the Hanford facility, sitting in an office in New York, whose unpublished doctoral homework literally holds the key to the atomic age. That dramatic rescue is basically just a tiny footnote in her life, because a little over a decade later, this exact same woman would design an experiment that completely rewrote the fundamental laws of the universe. She would prove, to the absolute shock of Albert Einstein and every other physicist alive, that the universe is actually slightly left-handed. And her reward for shattering everyone's understanding of reality? Watching two of her male colleagues walk up to a podium in Stockholm to accept the Nobel Prize in physics, while she was entirely, intentionally excluded. How do you save the world, rewrite the laws of physics, and get erased from the very history you made? If you are fascinated by the hidden shadows of history and the undeniable brilliance of the forgotten, make sure to like this video, subscribe to Legendary Lives Unveiled, and join us as we open the declassified archives to reveal the tragic, dramatic life of Dr. Chien-Shiung. To understand the sheer force of will that defines her life, we must go to a world that feels light years away from modern physics. She was born in the small town of Luyi, in the Jiangsu province of China, on May 31st, 1912. This historical timing is incredibly significant. It is the exact year the Republic of China was founded. The violent, hopeful birth of a brand new republic, following the collapse of the Qing dynasty and the end of thousands of years of imperial rule. She was born into an era where the horrific practice of foot binding was still a very recent living memory. Having only been formally banned around the time of the revolution, the cultural expectation for women was entirely centered on domestic obedience and preparing for marriage. Formal education for girls was considered useless or even dangerous. Yet, she had the immense fortune of being born to highly progressive parents. Her father, Wu Zongyi, an engineer and fierce political activist who had participated in the revolution, recognized that the new republic needed to educate its historically suppressed women to survive. In a wildly radical move, he founded the Mingdi Women's Vocational Continuing School, one of the very first schools dedicated entirely to girls in China, allowing them to learn mathematics, literature, and science, while societal expectations demanded they stay quiet in the kitchen. This visionary mindset extended to her naming. In traditional families, a generation character was strictly reserved for the boys, but her parents gave it to her anyway. Her full name, Chien-Shiung, translates roughly to heroes and outstanding figures, and she lived up to it. As a teenager, at a highly selective boarding school in Suzhou, and later at the National Central University in Nanjing, an incredible duality emerged. On one hand, she was a studious, meticulously quiet physics student. So hungry for knowledge, she secretly borrowed math and physics books to study alone in the middle of the night. On the other hand, she was a fierce political activist. In 1931, when Japan invaded Manchuria, and the Chinese government under Chiang Kai-shek adopted a policy of non-resistance, the student population was outraged. Wu emerged as a massive student leader, organizing massive sit-ins right at the presidential palace in Nanjing. The student organizers strategically chose her because her flawless academic record acted as a literal shield, knowing the government would hesitate to arrest such a highly regarded scholar. But to play at the highest levels of experimental physics, inspired by the biographies of Marie Curie, she knew she couldn't stay in China, where graduate-level programs simply did not exist. In 1936, at the age of 24, with financial support from an uncle, she boarded the steamship SS President Hoover, heading for America. The plan was simple: get her PhD, gain lab experience, and return to build China's scientific infrastructure. When she stood on that deck in 1936, waving goodbye to her parents and uncle, she had absolutely no idea it would be the last time she would ever see them alive. Less than a year later, Japan launched a brutal invasion of China, sparking the Second Sino-Japanese War, which bled directly into World War II. After the war ended, the Chinese Civil War escalated, leading to the communist takeover in 1949. The geopolitical walls slammed shut. For 8 agonizing years during the war, she couldn't even get a letter home, carrying the silent, terrifying weight of not knowing if her family had survived the bombings. She wouldn't be able to return for almost 40 years. In America, new obstacles awaited. She originally planned to attend the University of Michigan, but while visiting UC Berkeley in San Francisco, another Chinese physics student named Luke Chien-Shiung casually mentioned that at Michigan, women were forced to use a side door at the newly built student union. The girl who led protests outside a presidential palace was disgusted. She abandoned Michigan on the spot and enrolled at UC Berkeley. Berkeley was the absolute epicenter of nuclear research. She studied under Ernest Lawrence, soon to win a Nobel for inventing the cyclotron particle accelerator, and Emilio Segre, another future laureate. In this intensely male-dominated environment, Wu became a phenomenally meticulous experimentalist. Her doctoral thesis mapped out the radioactive products of uranium fission, specifically tracking the isotopes of xenon gas, and conducting foundational research into beta decay. By the time she earned her PhD in 1940, she was widely considered one of the most brilliant experimentalists alive. J. Robert Oppenheimer, the future father of the atomic bomb, was on her committee and affectionately called her Jieji, elder sister in Chinese. Yet, when she graduated, the reality of profound anti-Asian racism and institutional sexism collided with her brilliance. With Pearl Harbor attacked in 1941, anti-Asian sentiment reached a fever pitch, and despite glowing recommendations from Nobel laureates, no major research university would hire her. She was locked out of the laboratory, forced to take a teaching position at Smith College, a women's college lacking the multi-million-dollar particle accelerators she needed. It was an incredibly frustrating exile, like forcing a master watchmaker to teach middle schoolers how to use a sundial. She eventually made history as the first female faculty member at Princeton University, though primarily teaching naval officers, not doing her own research. In 1942, she married Luke Chien-Shiung at the California home of physicist Robert Millikan. Completely cut off from their homeland during the raging Pacific War, neither family could attend. Luke was the grandson of Yuan Shikai, the first formal president of the Republic of China, hailing from an almost royal political family. Yet, Wu steadfastly refused to take his name. It was unheard of in the 1940s. But if colleagues called her Professor Yuan, she sternly corrected them. "I am Professor Wu." Her scientific exile ended abruptly when the top-secret Manhattan Project, racing to build the atomic bomb before Nazi Germany, found itself desperately short on top-tier physicists. In March 1944, this Chinese immigrant, who faced daily discrimination and wasn't even a U.S. citizen yet, was recruited into the Substitute Alloy Materials Lab, or SAM Lab, at Columbia University. She was likely the only Chinese person to work on the project. Her monumental task was uranium enrichment, developing the gaseous diffusion process to pull the slightly lighter, highly reactive uranium-235 out from the stable uranium-238 by pumping highly corrosive uranium hexafluoride gas through miles of porous barriers, which brings us back to the suffocating panic at the Hanford B reactor. The massive graphite and uranium machine, built to breed plutonium, was inexplicably dying and reviving like a breathing, choking entity. Fermi was panicking. He consulted Emilio Segre, who looked at the problem and simply said, "Ask Miss Wu." The very establishment that had marginalized her was now desperately dependent on her. When Wu looked at the Hanford data, she recognized a pattern from her lonely experiments with the Berkeley cyclotron. She knew that when uranium-235 splits, it creates an isotope called xenon-135. Wu had discovered something unknown to the rest of the world. Xenon-135 has an unprecedented appetite for absorbing neutrons, the oxygen of a nuclear chain reaction. As the reactor ran, the Xenon-135 acted like a chemical fire retardant, soaking up the free neutrons and poisoning the reaction. But because Xenon-135 is unstable, it would slowly decay over 9 hours when the reactor shut down, allowing the oxygen to return and the reactor to start again. Her unpublished college notes provided the exact cross-section measurements needed. The engineers crammed more uranium into the core to overpower the xenon poisoning. The reactor stabilized, and she literally saved the atomic bomb project. But the devastating toll of Hiroshima and Nagasaki, which killed up to 226,000 people, placed a profound moral burden on her. While initially driven by the fear of the Nazis getting the bomb first, the destruction deeply affected her. She entirely distanced herself from military weapons, refused to work on the hydrogen bomb, and in 1962, privately and explicitly advised Taiwan's president, Chiang Kai-shek, never to pursue a nuclear weapons program. She had seen the catastrophic asymmetry of power those weapons created, and she wanted no part in proliferating it. She had saved the Manhattan Project, but the shadows of the atomic bomb forced her to make a profound choice. She turned her back on weapons of war, shifting her focus to the pure, fundamental mysteries of the universe. Stepping down into a damp New York basement to hunt for microscopic ghosts, and preparing to prove a concept that Albert Einstein himself despised. In the late 1940s, while the world was still grappling with the devastating aftermath of the atomic bombs she had helped build, Dr. Chien-Shiung quietly shifted her gaze away from weapons of war. She descended into the damp, quiet basement of Pupin Hall at Columbia University, preparing to confront a theoretical ghost that Albert Einstein himself famously despised. In 1949, working alongside her graduate student, Irving Shaknov, Wu conducted the first ever experimental validation of quantum entanglement. Einstein had mockingly called it spooky action at a distance, the bizarre, science fiction-like idea that two subatomic particles could become so deeply connected that measuring one instantly and inevitably affects the other, no matter how far apart they are. Even if one particle is on Earth and the other is on the opposite side of the Andromeda Galaxy, measuring one instantly defines the state of the other. It seemed to imply that information was traveling faster than the speed of light, violating our most basic understandings of space and time. Theoretical physicists like Einstein, Boris Podolsky, and Nathan Rosen had furiously debated this concept on chalkboards throughout the 1930s. But it was purely theoretical philosophy. How do you actually prove something that weird in a physical lab? Wu and Shaknov did it by studying electron-positron annihilation. Imagine two billiard balls on a table. One is an electron, regular matter. The other is a positron, antimatter, its exact opposite. When these two particles collide, they do not bounce off each other. They completely, violently cease to exist. They annihilate, shooting out two flashes of pure, high-energy light photons in perfectly opposite directions. Because those two photons were born from the exact same annihilation event, quantum theories suggested they should be entangled. Wu's painstaking experiment measured the polarization, the specific orientation of these paired photons as they flew apart. She proved that they were, in fact, correlated in exactly the way quantum mechanics predicted. If one photon was spinning a certain way, the other was locked into the opposite spin. She had practically birthed the experimental foundation of quantum entanglement, the literal bedrock of the multi-billion-dollar quantum computing and cryptography industries we are building today. Yet, because quantum information science didn't exist as a field in 1949, the establishment simply looked the other way. Her early proof was buried in the archives. It wouldn't be until decades later, following the 2022 Nobel Prize in Physics, that Lars Brink, a former chair of the Nobel Committee, publicly stated that Wu's 1949 experiment was a foundational gem of physics that had been completely overlooked. But even if the world missed her quantum breakthroughs, the physics community bowed to her absolute, terrifying authority in another realm: beta decay. Beta decay was her true kingdom. Back in the 1930s, Enrico Fermi had proposed a beautifully elegant mathematical theory, explaining how an unstable atomic nucleus spits out an electron to stabilize itself. But for 15 years, experimental physicists all over the world kept producing data that contradicted Fermi's theory. The energy levels of the escaping electrons were all wrong. The physics community was in absolute turmoil, with theorists proposing all sorts of ugly, complicated Frankenstein theories to explain the flawed data. Dr. Wu stepped in, analyzed the experimental setups of her male colleagues, and realized the problem wasn't Fermi's beautiful theory. The problem was that the other experimentalists were just sloppy. First, they were using radioactive targets that were too physically thick. As the electrons tried to escape, they literally bounced off other atoms and lost energy, like trying to run a sprint through a crowded hallway instead of an empty track. Second, the men were using magnetic spectrometers with heavy iron cores, which created a magnetic memory, or hysteresis, giving them completely false readings. We refused to accept flawed data. She tracked down an old iron-free spectrometer built before the war. Then, she spent an agonizing amount of time creating microscopically thin radioactive films, eliminating all the scattering errors that had baffled the men in her field. She ran the experiment again. The result? Enrico Fermi was perfectly right all along. The anomaly was merely an illusion caused by bad equipment. Her rigorous precision became so legendary that prominent physicist Maurice Goldhaber joked that people avoided doing experiments in beta decay simply because they knew Chien-Shiung Wu would do a better job than anybody else. So why bother trying? There became an actual famous saying among scientists at the time: if the experiment was done by Wu, it must be correct. It was exactly this reputation, the ultimate, undisputed arbiter of physical reality, that led two desperate theoretical physicists to knock on her office door in the spring of 1956, setting in motion the most dramatic, history-altering, and deeply infuriating moment of her entire life. To understand the massive gravity of what they asked her to do, we must understand a bedrock concept of science: the law of conservation of parity. For decades, physicists believed there was a fundamental symmetry to the universe. Parity dictates that the laws of physics are exactly the same in a mirror image world. Imagine holding a mechanical clock up to a mirror. The visual image is flipped, the numbers are backward, and the hands appear to spin counterclockwise. But the mechanical rules governing the gears inside, making the spring uncoil and the clock tick, operate exactly the same way. The mirror doesn't change the underlying laws of physics. For the electromagnetic force, the strong nuclear force, and gravity, parity holds perfectly true. Physics absolutely does not care about left or right. But in the mid-1950s, a strange mystery emerged in particle accelerators known as the tau-theta puzzle. Two subatomic particles, the tau and the theta, appeared to be completely identical. They had the exact same mass and the exact same lifespan, but they decayed in completely different ways. One decayed into two particles, the other into three, blatantly violating the rules of parity. Enter the two desperate theorists, Sung-Dao Lee at Columbia and Chien-Ning Yang at Princeton. They looked at this puzzle and proposed a wild, almost heretical idea. What if the law of conservation of parity does not apply to the weak nuclear force? What if, in the strange realm of radioactive beta decay, The universe actually does distinguish between left and right. It was a shocking hypothesis. It was like suggesting that the mirrored clock didn't just look backward, but actually ticked at a completely different speed. Because the universe secretly favored right-handed gears, Richard Feynman even bet $50 that parity would not be violated. But Li and Yang were theorists. They worked with math on chalkboards. They had an idea, but absolutely no way to build an experiment to prove it in the real world. So Li walked down the hall and asked Dr. Wu for help. Because she was a genius, Wu immediately realized the magnitude of the request. If they were right, it would shatter the bedrock of physics. She had to do this experiment, and she had to do it now, before anyone in Russia or Europe beat them to it. But to do it, she had to make an unimaginable personal sacrifice. The timing was deeply, tragically poignant. For the summer of 1956, Wu and her husband Luke had planned a massive, long-awaited trip. They had booked tickets on the ocean liner Queen Elizabeth to travel to Europe, and then, finally, to the Far East. She was going home. She was finally going to see her parents in China. She hadn't seen them since she waved goodbye from the deck of a steamship in 1936. 20 years of war, isolation, and agonizing waiting. The tickets were literally in her hand, but she realized that if she took the trip, someone else might claim the discovery of the century. So, she made the ultimate sacrifice for science. She told her husband to go without her. She canceled her ticket, stayed in America, and went to work. The experiment was an absolute engineering nightmare. To test if beta decay had a left-right preference, she needed to observe a radioactive isotope called cobalt-60. But atoms are constantly vibrating because of thermal heat. To test for parity, she needed to overcome this thermal jitter and align the magnetic spin of every single cobalt-60 nucleus in the exact same direction, allowing her to see if the electrons shot out up or down relative to that spin. The only way to stop atoms from jittering is to freeze them. She needed to cool the sample down to a fraction of a degree above absolute zero, minus 459 degrees Fahrenheit, or 0.01 degrees Kelvin. It is the coldest possible temperature in the universe, where all atomic movement basically stops dead. Wu was not a cryogenics expert, so she collaborated with Ernest Ambler from the Low Temperature Group at the National Bureau of Standards in Washington, D.C. For months, she commuted between New York and D.C., working grueling, sleepless nights while constantly battling the physical equipment. Trying to put a radioactive source inside a supercooled vacuum flask surrounded by liquid helium was terrifying. The glass vacuum tubes kept leaking. The liquid helium kept boiling off too fast. The electrons she was trying to measure somehow had to escape the thick walls of the cryostat, just so her detectors could see them. But eventually, she cracked it. In the freezing days of December 1956, having practically moved into the laboratory, the data stabilized. The magnetic fields were applied. The cobalt-60 nuclei were aligned. As they underwent beta decay, they spat out electrons. If parity was conserved, if the universe was a perfectly symmetrical mirror, the electrons should have fired off equally in all directions, 50% up and 50% down, regardless of the nuclear spin, but they didn't. The data was glaringly irrefutable. A significant majority of the electrons were firing off in one specific direction, opposite to the spin of the nucleus. The symmetry was broken. The universe, at its most fundamental subatomic level, is slightly left-handed. When the results were formally announced in early 1957, it sent an absolute shockwave through the global scientific community. The New York Times put it on the front page. Wolfgang Pauli, a famously arrogant physicist, was in total disbelief. Because the discovery was so paradigm-shattering, the Nobel Committee moved with unprecedented speed, abandoning their usual practice of waiting decades. By the end of 1957, the Nobel Prize in Physics was awarded for the discovery of parity violation to Tsung-Dao Li and Chien-Shiung. Dr. Chien-Shiung Wu, the woman who canceled her trip home to see her parents, the woman who conceptualized and designed the impossible experiment, who spent months freezing in a D.C. lab battling liquid helium, and who actually proved the theory was real, was entirely, intentionally excluded. The omission of Dr. Wu is still considered one of the most egregious, embarrassing snubs in the history of the Nobel Prize. The theories of Tsung-Dao Lee and Chien-Shiung were brilliant, certainly, but they were purely theoretical, as Lee himself freely acknowledged later, without Wu's experiment. Their theory was just mathematical speculation on a chalkboard. For decades, defenders of the committee hid behind a profound misunderstanding of physics. They argued that theorists dream up the concepts, while experimentalists merely do the plumbing. But in theoretical physics, theorists throw out hundreds of ideas a year, and most of them are wrong. Lee and Yang proposed a question. Is parity conserved in weak interactions? It was Wu who provided the actual answer. Designing an experiment at near absolute zero to measure beta decay asymmetry wasn't plumbing. It required inventing entirely new experimental techniques, dragging the theoretical into physical reality. So, was it a catastrophic bureaucratic oversight or deeply ingrained institutional sexism? For 50 years, thanks to the rules of the Nobel Foundation, their archives remain strictly sealed, leaving the world to guess. But recently, as we have gained access to the newly opened 2026 archives detailing long-term nomination patterns, the truth has finally come to light. In 1957, the year the prize was awarded, Dr. Wu was not nominated at all. The reason was a strict, inflexible bureaucratic deadline. Her groundbreaking paper, Experimental Test of Parity Conservation in Beta Decay, was published in the Physical Review on February 15, 1957. The absolute deadline for Nobel nominations for that calendar year was January 31st. She missed the deadline by a mere 2 weeks. Lee and Yang had published their theoretical paper months earlier in 1956, making them eligible and heavily nominated. The Physics Committee adopted a highly conservative, narrow stance, choosing to reward the theoretical insight immediately, rather than waiting for the experimental validation to clear the bureaucratic timeline. However, that procedural hiccup absolutely does not excuse what happened next. The Nobel Committee is fully allowed to award prizes for past discoveries. They could have simply awarded her the prize the very following year, in 1958, and the physics community tried to force them to do exactly that. Over the next 16 years, Chien-Shiung Wu received no fewer than 23 separate Nobel nominations. 18 different leading physicists nominated her. Tsung-Dao Lee, the man who won the prize, nominated her himself 3 separate times, explicitly writing to the committee that her experimental work was vital and deserved recognition. But the committee wouldn't budge. Internal memos reveal a stubborn, almost defensive refusal to retroactively include her, with some members arguing that because she was testing a theory proposed by others, her work wasn't original enough. It was a staggering, entirely hypocritical double standard. As historians note, male physicists James Cronin and Val Fitch won the Nobel in 1964 for an experimental discovery, testing a theory. Yet Wu, who executed a far more difficult and fundamental experiment, was continually passed over. The archives paint a clear, damning picture of a conservative, male-dominated committee hiding behind rigid procedures to avoid acknowledging a monumental mistake. They gave the prize away too fast and refused to admit they left the most important person out. She proved the universe was physically asymmetric, and in return, the scientific establishment showed her just how asymmetric its own reward system was for women. Publicly, she maintained incredible grace. She continued to work with Lee and Yang, remaining lifelong friends and never publicly trashed the committee. But privately, it was a deep, enduring wound. Years later, in a letter to Jack Steinberger, a fellow physicist and Nobel laureate who frequently championed her cause, she wrote, "Although I didn't do research just for the prize, it still hurts me a lot that my work was overlooked for certain reasons. For certain reasons, she knew exactly what was going on, but she refused to let a gold medal in Stockholm define her legacy. If anything, the snub ignited something even fiercer within her. In the 1960s, she became an absolute, unstoppable force. Following the parity experiment, theoretical physicists were scrambling to build a unified theory of the weak interaction. 2 absolute legends of physics, Richard Feynman and Murray Gell-Mann, proposed the conserved vector current hypothesis, or CVC. CVC proposed that the weak nuclear force was intimately connected to the electromagnetic force, a huge step toward unifying the forces of nature. But once again, it was just a beautiful theory that desperately needed experimental proof. And once again, they knocked on Dr. Wu's door. In 1963, she executed another incredibly delicate beta decay experiment, comparing the subtle differences in the decays of two specific isotopes, boron-12 and nitrogen-12. The measurements had to be unfathomably precise, and she pulled it off, perfectly validating the CVC hypothesis. This specific work laid the fundamental, concrete groundwork for what we now call the Standard Model of particle physics, the overarching theory describing all fundamental forces and particles in the universe. She was essentially the physical architect of modern physics, and her intellectual curiosity was completely boundless. She realized the quantum tools used to study the atomic nucleus could be applied to human biology. She pioneered the use of the Moosbauer effect, a phenomenon where atomic nuclei absorb and emit gamma rays without recoiling, allowing for unbelievably precise measurements of an atom's chemical environment. Wu took this technique and applied it to iron atoms inside hemoglobin molecules in human red blood cells. She used the tools of quantum mechanics, the very tools of the atomic bomb, to research the molecular deformations causing sickle cell anemia, advancing human medicine in profound ways. As she grew older, she became fiercely outspoken against the discrimination that had tried to hold her back. In 1964, at a massive MIT symposium focusing on women in science, she stood at the podium and delivered a sharp, witty line to a room full of male scientists. "The atoms don't care if you're a man or a woman. So why does the scientific community?" She fought for structural changes. In 1975, she discovered she was being paid significantly less than her male counterparts at Columbia University. The woman who proved parity violation, who validated CVC and saved the Manhattan Project, was making less money than the men teaching undergrad physics. She demanded retroactive parity in her salary, and she won. That exact same year, she shattered another glass ceiling, becoming the first female president of the American Physical Society. Accolades finally poured in. President Gerald Ford awarded her the National Medal of Science in 1975. She was the inaugural recipient of the Wolf Prize in Physics in 1978. She became the first living scientist to have an asteroid named after her, Asteroid 2072 Wu Chien-Shiung. But her most meaningful and most painful journey happened in 1973. Following President Richard Nixon's historic visit to China in 1972, relations slowly thawed. After almost 40 years of exile, Wu and her husband finally secured permission to travel back to her homeland. It was a heartbreaking homecoming. The geopolitical tragedies of the 20th century crashed down on her all at once. She discovered that her progressive father and supportive mother had passed away years earlier. Her older brother, her uncle who bought her original steamship ticket, and her younger brother had all perished during the violent, anti-intellectual chaos of the Cultural Revolution. Most painfully, her parents' physical tombs had been desecrated and completely destroyed by the Red Guards, simply because she was living in America. To spend your life in cold, damp basements unlocking the secrets of the universe, only to return home and find your family gone and their graves erased, is an unfathomable emotional toll. The destruction was so severe that the Chinese premier, Zhou Enlai, met with her personally to formally apologize. Did it break her? No, it actually emboldened her. She continued to advocate fiercely for human rights globally. She publicly protested political imprisonment in Taiwan under Chiang Kai-shek's regime. Years later, she strongly condemned the Chinese government's violent crackdown on pro-democracy students at Tiananmen Square in 1989. The same 19-year-old girl who led student protests in 1931 was still speaking absolute truth to power in her 70s. She spent her final years tirelessly advocating for STEM education, particularly for young girls traveling across the U.S., Taiwan, and China. Dr. Chien-Shiung Wu passed away from complications of a stroke in February 1997 at the age of 84. In a beautiful, full-circle conclusion to a life defined by exile, Her ashes were returned to China. They were buried in the quiet courtyard of the Mingdi Women's Vocational Continuing School, the very school her father founded, where she had first learned to read and write. She once said, "There is only one thing worse than coming home from the lab to a sink full of dirty dishes, and that is not going to the lab at all." She faced rampant anti-Asian racism, institutional sexism, lost her family to the Cold War, and was denied the greatest prize in her field by a committee of men who couldn't see past their own biases. But she kept going to the lab. She simply refused to be stopped. Until an experimentalist builds the machine, cools the atoms to absolute zero, battles the leaking helium, and actually observes the universe in action, a theory is just a guess. Wu was the ultimate arbiter of physical reality. Today, in 2026, we live in a world that absolutely worships the idea makers, the flashy theorists and tech CEOs. But somewhere, right now, there are modern-day Chien-Shiung Wus. They are laboring in windowless underground labs, fighting ingrained institutional biases, doing the grueling, unglamorous work of actually proving what is real in quantum computing, AI, or bioengineering. Science isn't just made by the people who draft the shiny blueprints. It is made by the people who actually pour the concrete. If this story changed the way you see history and the names printed in our science textbooks, make sure you hit the like button, share this video with a friend who loves hidden history, and subscribe to Legendary Lives Unveiled. We are dedicated to bringing you the incredible, untold stories of the people who actually built our modern world. Leave a comment below. Did the Nobel Committee make the biggest mistake in scientific history by excluding Dr. Wu, or were they just following the rigid rules of their time? You can try to erase someone's name from a gold medal, but as Dr. Wu proved, you can never hide the fundamental truth of the universe.